we go back to, these are our SAT scores again, okay? And so we're calculating the value or the probability that Z is between 0.68, minus 0.68 and 0.68, okay? If you'll recall from what we talked about the other day, because the probability that Z was 0.68, okay, created the probability that we had there, okay? So skipping ahead, all right, so here's what you have. And you're looking for the area under here. If you get the probability for 1707 and 1687, these are SAT scores. By the way, this is math. I looked it up. This is math and verbal and written. That's why these scores are in that range. All right. So what's the probability? You're going to get 1687 to 1707. You just subtract what's under this curve from this curve, and you're home free. 0.4714, if you did that. Here we go. So if you got more, yeah. If you increased your sample size, what have you done? In theory, not by calculations. What have you done when you increase? Whenever you take a sample, okay, and you get closer to the population, what have you done?
Made it more accurate.
That's exactly right. That's exactly right. That's the takeaway from this chart. Don't worry about the calculations, because it stands to reason. If your population is 200 and your first sample was at 40, and your second sample is at 100, you're going to be more accurate. And you're not going to get as much variation, so you're going to get a curve that's a little more beaky, okay? Because there's not as much variation, okay? Yep, and there you go. The more accurate you become, the less variance you have, because you're closer to understanding or calculating the overall population. So it stands to reason that you would have less variance or standard error. All right. Here we go. This is we're calculating at 100. So now n is 100. All right. Close to the population, so your sigma sub x, your standard deviation or your error, is going to be lower. And here's what you have. So now the area under this curve is 0.776. Because you've got a better sample size. So you're now 0.776, so you're more accurate than you were before. That's exactly right. Good. All right, now take this as an exercise and run with it. Same thing as we had before, using the same numbers. Good stuff. It really is. And this is the way the real world works. And like I said, what people do, everybody has their level of risk that they're willing to accept. There we go. All right. So now we're just dealing with proportions. And it's just nothing more. All we're doing is taking a number that was a whole number or near to whole numbers, and we're just taking, okay, what's 30 divided by 40 as a proportion of a population? If you had 40 people out there and 30 of them said everything was great, what proportion would you have? 0.75, that's exactly right, 75%. That's all we're doing here. No difference. The formulas are slightly different because you're dealing with a proportion, okay? But for the most part, the proportion is the proportion. And so very similar to what we had before is we're going to do a point estimate. And then we're going to infer, we're going to take that proportion just like we took a number before, okay, that was not a proportion necessarily, and we're going to infer that about the proportion of the overall population. Very simple, very straightforward, if you understood what we've gone through previously. As far as taking, and here you're going to do the exact same thing. You're going to take everything to a scale of z, except now you're going to use a slightly different formula. Just as we had before, the expected value of that sample proportion is going to be the population proportion. Same old before we talked about the expected value for x bar. It's going to be the population x bar as well. In this case, we're talking about proportion. And we're going to mostly work, I think the example I have here, let's keep working with infinite populations. An infinite population just means that it's either a very, very large number or it's just incalculable as far as what the overall population is. Okay? And as they say here, this is just the, hold on. As they say here, this is just the kind of a correction factor when you're dealing with a finite as opposed to an infinite population. Good enough? Nothing's changed. The only thing that changes is we're using a p instead of an x, and we're using a slightly different formula. That's it. And now you're actually picking up sigma sub p instead of sigma sub x bar. It's actually, I think there's probably, I'm going to go p bar on this one. That might be a Schulteism, by the way, sigma sub. But you have to use the standard deviation, not of the overall population, which you've been given. You have to convert that to the standard deviation for the distribution associated with p bar, or x bar, as you did before. All right, I don't want to go through this too much. All right, but let's take our St. Andrews campus. This is the SAT scores again. Same old, same old. The only difference is we're going to start using proportions instead of actual SAT scores. And you'll see here, okay, that n is equal to 30, okay, and p is equal to 0.72, okay, and p in this case is probability, and the reason you know that is it's italicized. All right. Now that we know that we're good to go, we have no problems with the n value not being high enough or not being too low. You can go straight into this calculation here, which is the formula for sigma sub p distribution, p bar distribution. Expected value is 0.72, and we're off to the races. Do the upper limit as before, 0.72 and 0.77 and 0.72. You calculate the z value, the upper limit and the lower limit. You'll find that that's 72%. If you went into the z table, as we have done many, many times, 0.61, 0.73. Or 0.7291 to be exact. So the area under this curve is 0.7921, about 73%. So So what that says is about 77% of this sample is has a probability of, or 72%, there's a 72% probability that you're going to get a proportion less than 0.77. And we do the lower limit just as before. All right, 0.2709. And there we go. Now, we've got this area under the curve, and what are we trying to isolate? The value between 0.67 and what was it, 0.77 over here? Yeah. And so we're going to isolate that. And we just subtract the two numbers out, and 45%. So now you can say there's a 45% probability that the applicants wanting on-campus housing will be between plus or minus 5%. Remember how, and by the way, that's another good way to look at it. Plus or minus 5%, you ever see on surveys where they go plus or minus 3% error? That's what they're talking about here. And we're p.05. All right, so here's what that looks like. Get those values, and you just, what you did again, once again, all you did was you isolated the area that is of interest to you. Okay. Now, oh, here's one. If this were a uniform distribution, what would this look like? What would you not have if this were a uniform distribution? What portion of this curve? Remember, uniform distribution is straight across, and this is a normal distribution. All you'd have to do previously is you just have to take the base times the height, but you can't do that here because you got all this additional activity going on up here relative to probability. Make sense, Caitlin? Okay, good. All right, everybody got it? Ashley, you okay? Okay. Okay, Benjamin? One of my best friends from college name is Benji. So, all right. So you took everything to a scale of z using just a slightly different formula because you're using proportion, okay? And you made sure that your values of n were proper. Okay. And then you did the exact same thing you did before. So now I want you to go to 732A, page 326. And it should be a proportion. Page 326